This is submodule 3 of 3 of the anti-collision series, so let's dive in. Having already reviewed survey inaccuracies, ellipsoids of uncertainty, and anti-collision fundamentals, this module focuses on the application of tools and practical methods. As drilling environments become increasingly complex, engineers rely on structured processes and visualization techniques to manage collision risk. This session emphasizes how to use anti-collision worksheets, plots, and advanced visualization tools to assess and mitigate hazards. We will also examine strategies for mitigating collision risk, including survey design, resurveying offset wells, and enhancing measurement accuracy. Another key focus is the concept of target sizing, which ensures the driller has a precise operational window based on geological targets and survey uncertainty. By the end of this module, you should be able to integrate theoretical understanding with practical application, confidently using the tools provided to reduce uncertainty and improve decision-making. The anti-collision worksheet is a structured planning and monitoring tool that helps drilling engineers assess risks and make informed decisions. It provides a framework for recording, calculating, and reviewing critical parameters related to separation factors, survey uncertainty, and proximity between wells. The worksheet serves as both a checklist and a decision-making aid, ensuring consistency across projects. It typically includes entries for subject and offset wells, survey data, error models, and calculated separation factors. By recording all inputs in one document, the worksheet makes it easier to identify patterns, potential errors, or unsafe conditions. During drilling, it can be updated in real time to reflect the most current survey data and recalculate clearances accordingly. This ensures operators do not rely on assumptions but make decisions backed by structured evidence. The anti-collision worksheet also facilitates auditability, as it documents the rationale behind operational decisions. Regulators and partners often require such documentation to verify that risks were assessed and appropriately mitigated. Ultimately, the worksheet helps transform complex survey and trajectory data into actionable information, bridging the gap between theoretical models and on-the-rig execution. Examining the survey sheet, the first detail to note is the header information. Is the slot location and coordinate system consistent with the well program? Next, as highlighted here, is the error model. Note here, circled in red, it reads Wolf and DeWart. This is an outdated error model, which is no longer in use. The error model used today is the ISCWSA error model. If any other error model is displayed, it should be questioned. Next, we have the subject survey listing. This is the listing of the planned well that we intend to drill. To the right, we have the offset survey. This listing is matched to the planned listing based on its TVD. This is required because different TVDs cannot collide. To the right of this is the azimuth direction of the offset well compared to the planned well. If we follow this, you can see that the offset starts approximately northwest of the planned well, then rotates through north and continues past the east direction. Then we have the center-to-center distance. To the right of this is the EOU distance. That is the distance from the edges of the error ellipses. You can see that initially this starts at 12.03 feet and reduces to as low as 4.38 feet. This is because as we gain inclination, the errors increase rapidly. Although our planned well is vertical to 900 feet, it is clear that the offset well has already deviated. As we talked about before, the separation factor is the center-to-center distance divided by the combined EOU of the offset and planned wells. When the separation factor goes below 1.5, this is a minor risk alert. When planning a well, we should make sure we are greater than this. In this example, the lowest separation factor is 2.04 feet, which is acceptable. We can also obtain anti-collision scans that incorporate all the offset wells of interest and highlight only the closest well for each 100 feet, providing the azimuth, center-to-center distance, EOU distance, and separation factor. Here we return to the spider plot, but this time with annotations. The plot shows multiple wells radiating outward from a central pad shown in red. The planned well is in green. Around each survey station, ellipsoids of uncertainty are drawn. The annotations provide additional clarity, identifying which well paths are offset, which are subjects, and where risk zones lie. The grid references include magnetic declination, grid convergence, and total correction, all of which ensure the plot is aligned with true coordinates. An annotated spider plot provides a visual overlay. If two EOUs overlap, annotations can highlight this as a red flag zone requiring attention. Or if you see the EOUs of one well increasing rapidly, this could indicate that the well has been surveyed with a tool that has a poor survey model. If this offset is close to the planned well, it may need to be resurveyed to reduce the risk. Additionally, the TVD depth markers are annotated, allowing the driller to cross-check for proximity at the same TVD. This tool is primarily a planning aid. It becomes more than just a picture. It would not be used in real-time anti-collision. The travelling cylinder is considered the primary anti-collision tool in crowded well environments because it updates clearance dynamically as drilling progresses. In this example, the subject well is displayed against offsets with major axis errors combined for both subject and object wells. The result is shown visually as the subject well appearing as a point centered in crosshairs on the plot. This makes interpretation quick and intuitive for the directional driller. Importantly, travelling cylinders are best used as live, computer-generated plots. Printing them on paper removes their real-time advantage and can lead to misinterpretation. They can be displayed in MTF mode or referenced to the high side when appropriate. In practice, this means the driller has an updated view of separation at all times while sliding or rotating. By summing the uncertainties from both wells, the tool ensures that the displayed separation accurately reflects reality. This makes the travelling cylinder plot not just a planning aid, but an execution tool that supports safe decisions in the high-pressure environment of navigating away from a platform with multiple slots. It is an essential safeguard when working in densely populated well fields. Continuing on the travelling cylinder plot, it offers a circular perspective, often described as a radar screen for well separation from the perspective of the planned well. The centre of the plot is the planned well. As we travel along the planned well, the distances of the offset wells are plotted. In this example, 3 offset wells are shown labelled A, B and C, along with error rings at depths of 400, 600 and 800 feet. The plot visualises its clearance at each depth. The coloured circles represent EOUs, showing zones of uncertainty. The strength of this method lies in its ability to enable directional drillers to quickly determine whether the subject well risks intersecting the uncertainty envelope of an offset at a particular depth. The tolerance lines drawn on the plot provide visual no-go boundaries, making it clear where risk exists. By comparing different depths, drillers can plan an exit trajectory that avoids potential conflicts. This tool is especially helpful in congested drilling pads or offshore platforms where wells are drilled close together. By using the travelling cylinder, we can make informed decisions about when to steer, slide, or rotate, ensuring separation factors are maintained and reducing collision risk. When looking at practical methods for mitigating the risk of wellbore collisions, the core idea is to increase the separation factor, a measure of the clearance between the subject and offset wells. The larger the separation factor, the safer the drilling. We can achieve this by increasing the centre-to-centre distance between wells at the planning stage, giving more margin for uncertainty. Another approach is improving survey accuracy, which reduces the size of the ellipsoids of uncertainty. Smaller EOU mean tighter confidence intervals and more reliable positional data. Where practical, we can also resurvey offset wells using high-accuracy gyroscopic tools, since many older wells were drilled with less precise equipment. Better data on their positions reduces the risk for the subject well. Finally, it is essential to plan for accurate survey tools during drilling. This could mean designing a survey program with fit-for-purpose equipment or using a survey-by-parts method to minimize cumulative error over long well sections. Recall that the separation factor is the ratio between the center-to-center distance and the combined EOU of the subject and offset wells. The higher the ratio, the safer the clearance. In practice, anti-collision planning is all about maximizing that margin. Survey by parts displayed as a tree diagram. The idea behind this method is to break a well bore into smaller survey sections, each with its own uncertainty budget. As you can see, different hole sections are labelled with survey tools such as gyro single shots, MWD, and continuous gyro. Each section adds uncertainty, but by restarting the error accumulation at each casing point, the total positional error at TD is reduced. The diagram shows how significant uncertainty axes increase with depth, but by applying survey by parts, we contain that growth. For instance, Part 1 covers the surface to around 3,000 feet, drilling first with an MWD tool, which has an error model propagation in red. Then a gyro is used. Part 2 ties into the most accurate survey, which is the gyro, and continues to about 7,500 feet. Part 3 carries the well deeper with its own survey plan. The value of this approach is clear. If we relied solely on one continuous error model from surface to TD, uncertainty could grow unacceptably large, shrinking the driller's targets and increasing the risk of not achieving the target with statistical certainty. Survey by parts is a structured way to manage accuracy, ensuring EOUs remain within tolerable limits and final well placement is reliable. It is essentially risk management in survey design. Shown is a detailed survey program broken into parts. The purpose of such a program is to ensure accurate positional data is gathered consistently throughout the well. Each section of the hole, from spud to total depth, is assigned a specific tool, vendor, frequency, and quality control requirement. In the example shown, Part 1 involves a gyro to the seabed and an MWD tool, which ties onto this and drills the 17.5-inch section. In Part 2, the section is cased, and a casing gyro is run, which provides more accurate results. When the 12.25-inch section is drilled, the MWD is tied onto the end of the casing gyro. As the 12.25-inch section is drilled, the MWD error propagates to a point that is unacceptable for drilling the top reservoir target, so a survey may be run to improve the error before drilling to the TD of the section, and so on. The key point of survey program is to have an error which is less than the geological target size. The slide illustrates how the driller's target is different from the geological target. In theory, the geologist defines a reservoir interval where the well should land. However, when we factor in the uncertainty of survey measurements, represented by the EOU, the effective target for the driller becomes smaller. In practice, this means we subtract the size of the EOU from the edges of the geological target. What remains is the driller's target, the zone within which we can place the well with high confidence, accounting for positional error. On the left, you can see this demonstrated graphically, with the green ellipse representing uncertainty carved out of the geological rectangle. On the right, multiple survey points with their EOUs create a cone of uncertainty along the well bore. This highlights why accurate surveys matter. The larger the uncertainty, the smaller the driller's effective target, and the harder it is to land successfully. By planning for survey uncertainty and setting realistic drillers' targets, we reduce the risk of missing the reservoir. It serves as a reminder that geology defines the where, but drilling must operate within tighter limits. Okay, let's recap the module on anti-collision. At this stage, you should be confident in explaining the root causes of survey inaccuracies and the different tests available to detect and reduce them. You should be able to discuss key terminology around uncertainty in well positioning, which underpins everything in anti-collision planning. You should also clearly define the ellipsoid of uncertainty, or EOU, and explain how it describes the range of possible well positions. Alongside this, you should be comfortable describing the travelling cylinder method and how it compares to spider plots in visualizing separation. Another essential learning outcome is being able to illustrate the various ways of plotting well paths and calculating distances between them, whether in 2D or 3D views. You should also understand how to interpret anti-collision plots and the importance of target sizing. Target sizing involves adjusting the driller's target to account for survey uncertainty, ensuring the well can be safely placed within the geological target. Finally, you should now understand what a comprehensive survey program entails, including survey frequencies, tools, and quality checks. This ends the module on anti-collision. I hope you have gained value from this. Please move on to the quiz. Thank you.